The next section in your textbook, section 7-4, starts off by describing the neuromuscular junction. So a stimulus for a muscle contraction arises from the nervous system, and the specialized intercellular connection between the nervous system and the muscular system is called a neuromuscular junction. And that nerve cell that controls a muscle fiber is called a motor neuron. The axon terminal of the neuron branches within the perimysium and contains vesicles of the neurotransmitter acetylcholine. So acetylcholine is the name of the neurotransmitter. And so you get this stimulus from the nervous system, and the neurotransmitter inside of the axon terminal will cross the synaptic cleft. The synaptic cleft is the space between the axon terminal and the sarcolemma, that specialized muscle fiber cell membrane. Okay, so the acetylcholine crosses the synaptic cleft, and what it does is it binds to the motor end plate. And this is a specialized receptors for acetylcholine on the sarcolemma. So the neurons stimulate the sarcolemma by generating an action potential. And an action potential is essentially an electrical impulse. So let's take a look at what this looks like.
An action potential arrives at the presynaptic terminal, causing voltage-gated calcium ion channels to open, increasing the calcium ion permeability of the presynaptic terminal cell membrane. Calcium ions enter the presynaptic terminal and cause vesicles to release their neurotransmitter acetylcholine from the synaptic vesicles into the presynaptic cleft. Diffusion of acetylcholine across the synaptic cleft and binding of acetylcholine to acetylcholine receptors on the postsynaptic muscle fiber membrane causes an increase in the permeability of ligand-gated sodium ion channels. The movement of sodium ions into the muscle cell results in depolarization of the postsynaptic membrane. Once threshold has been reached, a postsynaptic action potential is generated and is propagated over the muscle cell membrane. Acetylcholine is rapidly broken down to acetic acid and choline in the synaptic cleft by the enzyme acetylcholine esterase. The choline is reabsorbed by the presynaptic terminal and combined with acetic acid to form more acetylcholine, which enters the synaptic vesicles.
So that's an important thing to note there. The acetylcholine esterase is an enzyme on the motor end plate that breaks down acetylcholine, because that acetylcholine has to be broken down very quickly so that it doesn't continue to stimulate and keep those voltage-gated channels open. So that acetylcholine esterase is very important in breaking down the acetylcholine. So then that action potential is going to travel over the sarcolemma and down into the T tubules. Okay? And when that action potential rolls down into the T tubules, it's going to cause a release of the calcium ions from the sarcoplasmic reticulum. That's what SR stands for, sarcoplasmic reticulum. So you have all this calcium then flooding into that muscle fiber, and the calcium is important. Remember I told you calcium is the key. It binds to the troponin. Okay. So when calcium binds to the troponin, it causes that change of the troponin shape and pulls the tropomyosin off of the actin's active sites. And once that happens, the myosin can then bind to those active sites on the actin, and the contraction cycle can start. So let's take a look at what happens. Remember, in the last video we left off with an action potential traveling over the sarcolemma.
An action potential introduced at the neuromuscular junction is propagated along the sarcolemma of the skeletal muscle. At the T-tubule, the action potential is propagated on the T-tubule membrane into the interior of the muscle cell near the ends of the sarcoplasmic reticulum. The depolarization of the T-tubule membrane causes nearby voltage-gated calcium ion channels on the sarcoplasmic reticulum to open, resulting in an increase in the permeability of the sarcoplasmic reticulum to calcium ions. Calcium ions then diffuse from the sarcoplasmic reticulum into the sarcoplasm. Long filamentous tropomyosin proteins lie on two sides of the actin myofilament, covering up the sites where myosin can bind to the actin myofilament. Globular troponin proteins are attached to the tropomyosin. When calcium ions bind to troponin, this causes troponin to change conformation and move the tropomyosin. When the tropomyosin moves, this uncovers the myosin-binding sites on the actin, allowing myosin heads to bind and form cross bridges. The cross bridges play a role in muscle contraction.
And so now we've come full circle in our contraction description. Okay, so what's happening here is exactly what I was telling you about in the very beginning. These myosin heads are going to bind to the actin and slide closer together until those actins are so close together that this band right here is going to completely disappear. Okay. So again, you can replay these videos as many times as you want. All you have to do is go in and open up the actual PowerPoint file that's posted on Blackboard in the Learning Plans folder. And you can click on that link and it will take you right to this site. And you can play these animations as many times as you would like to. I think videos are a great way to describe what's happening, especially when you're talking about what's happening on the molecular level. So now that you're familiar with the contraction of individual muscle fibers, we can examine the coordinated contractions of an entire population of skeletal muscles. So as sarcomeres contract, so does the entire muscle fiber. And as fibers contract, tension is created by tendons pulling on bones. So movement will occur only if the tension is greater than the resistance. Okay. So resistance is just a little physics for you here. Resistance is just a passive force that opposes movement. So tension is a product of a number of cross bridges a fiber contains, and variation in tension can occur based on the amount of overlap of the myofilaments, the frequency of stimulation. The more frequent the stimulus, the more calcium ions are going to build up, and it can result in greater contractions. Whole skeletal muscle organs contract when its component muscle fibers are stimulated. And contractions are going to vary in their tension based on the frequency of muscle fiber stimulation and, again, the number of fibers activated. A single stimulus contraction relaxation cycle in a muscle fiber or a whole muscle is represented by a myogram, which is pictured on the next slide. And this cycle has three phases. It has a latent period, a contraction phase, and a relaxation phase. A single stimulation will result in a single twitch, but twitches in a skeletal muscle don't accomplish anything useful. All normal activities are going to require some sort of a sustained muscle contraction, such as from repeated stimulations. So this is the myogram that I mentioned in the previous slide, but this myogram has just a single stimulation, contraction, relaxation cycle in a muscle fiber. Okay, so let's take a look at these different phases. The first one, this latent period. So here on this axis we have the amount of tension, so an increase in tension, and down here we have time. And we have our different phases marked out for you. So at the point of stimulus to the point of contraction, that is the latent period. And you'll notice that there's no tension that is accrued here. And that's because at the point of the stimulus, you still need to generate that action potential. So you still need to release all your calcium iosins. You need to activate your troponin and your tropomyosin. And that all takes time. Okay, so that's what's happening during the latent period. But then, once you start to generate tension, you are then entering the contraction phase. Okay, so this is the development of tension. That's because all your cross bridges are developed and they're pulling. Okay. Once you start to lose tension, once that tension decreases due to the restorage of all those calcium ions and the covering up of all of your actin active sites, and that is officially the relaxation phase. Okay. So you have those three phases in a single stimulus, contraction, relaxations. So this is a twitch. This is one twitch. Now, if a second stimulus arrives before the relaxation phase has ended, then a second, more powerful contraction can occur. And the addition of one twitch to another twitch is called summation. Summation. And virtually all normal muscular contractions involve some form of incomplete tetanus then. So a near peak tension with very little relaxation before the next twitch or the next stimulus occurs. Complete tetanus is when you have stimuli that are so frequent that relaxation does not occur, and that's not necessarily ideal for a normal muscle activity. So here we have a couple more myograms that show the effects of repeated stimulations. Okay, so summation is the first one here. This is where you have your first original stimulus, you reach your maximum point of tension for that stimulus and you start to relax, but then before the relaxation phase is complete, you receive another stimulus. And so your second contraction produces even greater tension. As you start to enter relaxation, you get another stimulus which increases the tension. Another stimulus increases tension. Okay, so at that point you have enough tension to accomplish your goal and the relaxation period concludes. Okay, so this is an example of summation and how you can build tension by increasing the number of stimuli on a muscle fiber. Okay, over here we have an example of incomplete tetanus. So this is going to occur if the stimulus frequency increases even farther, and the tension production will rise to a peak, and the periods of relaxation in between are very, very brief. So we need to maintain that tension for a longer time. Okay, so this is an incomplete tetanus where you're having the relaxation phase begin, but then you're receiving another stimulus to maintain that tension. Okay, this is what a normal muscle contraction will look like to achieve a normal muscle coordination. And then during complete tetanus, over here at C, during complete tetanus, the stimulation frequency is so high that the relaxation phase is completely eliminated. And so the tension is going to plateau at a maximum level. So with varying numbers of fibers activated, you can have a smooth contraction and a lot of control. Most motor neurons control a number of fibers through multiple branching axon terminals, and so that is what a motor unit is. A motor unit is a single motor neuron and all the muscle fibers that it innervates. So motor units are typically dispersed throughout the muscle organ. And so this way you can recruit a graded addition of motor units to produce adequate tension. So recruitment is down at that second bullet point, but this is a mechanism for increasing your tension in a coordinated, smooth way, okay, to create a coordinated movement. And so when you need fine movements, when you need fine motor control, you're going to use motor units with very few fibers per neuron. So maybe one neuron, one fiber. Okay, so you have lots and lots of neurons involved in a fine motor control. But for gross movements, like picking up your textbook, you're going to have a very high fiber to neuron ratio where you have lots of fibers that will be controlled by just one neuron. Okay, so you see the difference between writing with your pen or lifting an entire book. Writing with your pen is a fine motor control, and so you're going to have very few fibers per neuron. So let's take a look at what that looks like. Here we have three motor neurons innervating this group of muscle motor units. And you can see to maybe to lift up your pen off your desktop, you need to just recruit these motor units from the red neuron. And notice how they are evenly dispersed throughout that muscle so that you can get a nice even movement so that you're not just pulling on one side of the muscle. Now, to lift your book, you might need all three of these motor neurons to be activated, and so you stimulate the entire muscles. Okay? And so that's a motor unit. A motor unit is all of the fibers that are controlled by just one neuron. So if this were, instead of from your biceps, if this were maybe down in your forearm for your fingers, for your digits, you'd have maybe just a ton of neurons here instead of just three. Maybe you'd have one neuron for each fiber. Okay, so those fine motor control movements require a lot more motor units and a lot more neurons. Now, some muscles at rest will still have a little bit of tension, and this is called muscle tone. The primary function of muscle tone is to stabilize joints and to maintain your posture. Atrophy, the next word listed there, the next vocabulary term for you, atrophy occurs in a muscle that's not regularly stimulated, and so your muscles will become small, they'll become weak. You can see this after you take a cast off of a limb and you haven't used any of those muscles for how many weeks. Those muscles have atrophied. So muscle contractions are typically classified by patterns of tension and how those patterns of tensions are produced. So for example, isotonic contractions are when the length of a muscle changes, but the tension remains the same until relaxation. So for example, when you lift that book, that's an isotonic contraction. Compare that to the muscle contraction you would experience if you're pushing against the wall. That's an isometric contraction. So the whole muscle length stays the same, because when you push on the wall, nothing's going to happen. But the tension that you're producing is still increasing. It doesn't exceed the load, but you can still increase your tension. Your muscle length stays the same. So that's isometric contraction. Now, elongation of your muscles after your contraction, after you're done with the tension, after you've accomplished your goal, elongation is typically a passive event. And so it uses a combination of gravity to pull that muscle back apart, elastic forces, and even opposing muscle movement. So when you're picking up a book and using your biceps brachii, you can then use your triceps brachii to then pull that elbow joint back into an extended position. Okay, so that's an opposing muscle movement. And so that brings us to a checkpoint and the end of this particular recording. Describe a neuromuscular junction, and don't be afraid to go back and review that video and any of the other videos as many times as you need.